Hello, and welcome to Agrosive Physics. Today is day 79, where we're going to look at wave characteristics and have an equation to determine the speed of a wave. Now, the first characteristic I'd like to look at is frequency. And what's important is that we understand the fact that in physics, many of the variables we're looking for will allow us to calculate certain other variables. Understanding that frequency represents the pitch of a sound wave is one thing. Being able to use it in an equation takes it to that next step. But frequency is how often the wave is going to vibrate. It's the number of cycles a wave vibrates per second. And we have an equation, if you would call it that, of cycles over time to represent the frequency. Now, one thing to note is that the speed of the wave is determined by the material in which it's traveling through. The frequency does not change how quickly a wave will travel through a material. If we think about a choral group, people who are singing high notes versus low notes, it would be very difficult if the high notes traveled faster to the audience than the low notes. We would have to sing in a manner where the high notes were first and then the low notes were slightly after them. And that's not how a choral group works. All the notes are sung at the same time to produce harmonies and melodies, and the wave will get to the audience at the same time. So even though there are different pitches of the sound waves being sung, they all travel the same speed in the air of the auditorium. So the frequency can be calculated by counting how often the wave vibrates up and down, one complete cycle, and determine how long it takes to do that. If it's 4 cycles in a second, the frequency would be 4. The units for frequency are either 1 over seconds, because cycles doesn't have a unit, it's just a number, or we simplify that to hertz. And the abbreviation for hertz is Hz. Now, we often compare light and sound in this course. And for sound, we already talked about the fact that frequency represents the pitch of the sound. With light, it's something a little less commonly known, and it's actually the color. Different colors of light have different frequencies. And in fact, if we get outside the visible spectrum, different types of light, different electromagnetic radiation, also have different frequencies. Ultraviolet radiation and infrared are different. X-rays and gamma have different frequencies. And all of these frequencies determine how they affect different tissues, if we're talking about human bodies, or different materials as they hit into the new materials. And remember, every time a wave hits a new material or a new boundary, 3 things happen: reflection, refraction, and absorption. Now, the frequencies of different instruments will look different. We don't always have a nice sine graph like we would in math class. In fact, different things like an electric guitar or a trumpet or a trombone will have different wave patterns. And that's why even the same note will sound differently with different instruments. And what I have here are a few examples of the different waveforms that are produced with different instruments. We have electric guitar, we have the trombone, and we have a trumpet. Now, each one of those will produce a certain wave pattern, and if we wanted to find the frequency, we would count the number of oscillations that occur, the number of patterns that we see, and divide it by the total time. So we could have 4 cycles in a fraction of a second, so 0.25 seconds. We would take 4 and divide it by 0.25. Well, in that case, it's 4 over a quarter, and we'd have 16 hertz. Now, each one of these waveforms is produced using a microphone. And if we put that waveform through a computer, it will form a visual representation of the sound wave itself. Higher frequency sounds will often look like it fills up the page more or the screen more than a low frequency sound. And of course, we can change the settings to affect how that looks on a computer monitor. But either way, the frequency is how often the wave vibrates. Now, since time is something that we often use in this course, we have the reciprocal of frequency, which is known as the time period. So if we take the frequency and do 1 over frequency, that will get us the time period. And just like we did when we talked about circular motion, we're going to use time period as a capital T. So the capital T will represent the time period, And if we think about the units of frequency, which was the hertz or 1/2, if we find the reciprocal of that, that's going to be seconds over 1. So of course, time period will be measured in seconds. Now, another characteristic of a wave is going to help determine the energy of the wave, and that's the amplitude, so the height of the wave. If we're thinking about a water wave, it's how high the wave is from its rest position. A higher wave, perhaps a wave that a surfer will be on, will have a much higher amplitude than the wave produced at, let's say, a lake. So the height of the wave will determine how strong the wave is. And in fact, the relationship between amplitude and energy is a direct square relationship. So if we double the amplitude, we'll actually quadruple the energy. Now, the amplitude is measured if we have a transverse wave from the rest position, typically the x-axis, to the top of the crest. Since waves are symmetric, we will have the same distance from rest to crest as we would from rest to trough. So we could measure the amplitude as well from the rest position to the bottom of the trough. But either way, the amplitude of the wave tells me a measure of how much energy the wave is going to have. Bigger waves, higher amplitudes, do not travel faster than lower amplitude waves. Once again, the speed of a wave is determined by the material in which it's traveling through. Now, we can determine the size of the amplitude if we merely measured the distance from vertically of a transverse wave from the x-axis to the height of the crest or to the bottom of the trough. And depending upon the scale, it could be in centimeters, it could be in millimeters, it could be in any unit that we measure the wave in. Now, comparing light and sound, sound waves use decibels as a measure of the amplitude. Light is brightness. Now, decibels are how loud the sound is, so we can adjust the volume and change the amplitude of the sound. With light, we can make it more bright. We can have a brighter light versus a dimmer light. Now, if we had a light switch on a dimmer, if we have it at the lowest setting, that would have low amplitude. And if we had it at higher setting, it would be a higher amplitude and it would be brighter. So as we adjust the voltage going to the light source, we can adjust how much amplitude or brightness the light has. Now, a few examples of the sound amplitude in decibels are a telephone dial tone or a power mower or a sun chip bag if we crinkle the sun chip bag. And each one of those will have different decibel levels. The unit for decibel, little d, capital B, is how we abbreviate that term. The higher the decibels, the louder the sound is, the more amplitude it has. And it's important to realize that you should often use ear protection when mowing or using power tools because those types of devices have high amplitude and can hurt your hearing. The brightness is measured in candela. And originally the unit was a marketing ploy based on using the incandescent light bulb, basically telling people that it was as bright as 2 or 3 or 4 candles. So we compared it to the brightness of a candle itself. Excuse me. So we compared it to the brightness of a candle itself. Now, waves in math class can have an equation. For example, if we have the equation x equals 7 cosine 4t, bits of that equation can tell us information about the wave itself. The number before the cosine is actually going to tell me the amplitude. We may not have the actual units in this case. It doesn't list the units, but that will tell me that whatever the amplitude is, it's 7 units high. The number before the t is a measure of, or can help us determine the frequency. It's just not directly like it is for the amplitude. If we take that number and set it equal to 2 pi f, that will allow us to find the frequency. So if you take that number, in this case a 4, and you divide it by 2 pi, that will tell me the frequency. Now, if you remember from math class, the reason 2 pi is important with waves is because that's the number of radians it takes to make one complete oscillation for a wave. So we take the number before the t, in this case, 4, divide it by 2 pi, which is how long it takes in radians to make one oscillation, and we can determine the frequency in hertz. So you can use a wave equation like you would in math class and pick apart the amplitude or the frequency, amplitude directly, the number before the cosine or sine, and the frequency indirectly with a slight calculation to find the frequency of the wave itself. If you were to graph that, it would change how it looks if we change the number before the cosine or we change the number before the t. And if you have a graphing calculator, you can try different numbers. Instead of a 7 cosine 4t, you can put in a 5 cosine 4t and see how the amplitude of that wave would change, and it would be smaller. You could also change how frequent the wave oscillates, and you can adjust that 4 to different numbers like 8 or 16 and see that it would increase the frequency in different cases. So waveforms that we may have learned in math class can be useful in physics as well, and we could take apart information from those equations to determine amplitude or frequency in this case. Now, another important term that we're going to need to know is phase. And phase is a measure of how the wave is vibrating with respect to other particles on the wave. We could have phase within a single wave, so particles along a wave can be in phase or out of phase, or we could have two waves that might be in phase or out of phase with respect to one another. If we have two different waves, the amount of phase will affect how they interfere with one another. And we'll talk about interference in a later discussion. For now, what's important is that you know that phase is how the wave particles are vibrating with respect to either other particles on the wave or with respect to other particles on another wave. If waves are, or if particles are in phase, or an entire wave can be in phase with another wave, that means they are moving in the same pattern. So the particles are at the same distance from rest, moving in the same direction at the same time. If you think about someone on a swing set with another person next to them, and they are swinging together on the swing set, that would be considered in phase. If they're swinging opposite one another, so one person is at the opposite end, they're at the up part of their swing while the other person is at the back part of the swing, they would be out of phase. In phase and out of phase are perfect situations where either the waves combine or interfere destructively. But you can also have partial phase. It could be sort of in phase or sort of out of phase. Now, instead of saying sort of, we have a more technical way to say that, and that is by listing the number of degrees you are either in or out of phase. Now, if you're in phase, we call that 0 degrees. You're with each other. If you're out of phase, you call that 180 degrees. You're completely opposite one another. Just like we talked about before with a crest and a trough. A crest is out of phase with the trough and as it inverts. If we have two crests, they would be considered in phase. If we're partially in phase or out of phase, the wave may combine in different ways. So if we're in phase completely, the waves would form a bigger wave. If we're out of phase completely, the waves would actually cancel each other out. But in either case, we have phase being how the waves are vibrating with respect to either particles on the wave itself or with other waves next to it, or perhaps in the same location at the same time. Now, because phase is an important aspect of the vibration of a single wave, we can use that to determine the wavelength of a wave. Now, in the diagram here, I have a situation where we have a single wave. This is a sine graph, or two sine graphs connected together, and we have different particles on the wave. And in this case, A and F would be in phase. They're doing the same thing at the same time. B and G would be in phase. E and J would be in phase. Now, other particles might be out of phase. For example, A and D are out of phase. B and E are out of phase. D and F are out of phase. C and H are in phase. And on the Regents exam or other examinations, you may find that there are questions that ask what particles are doing the same thing at the same time, in phase. What particles are doing the opposite from each other, out of phase. Now, it's important with this to realize that particles in a transverse wave only move up and down. So if we have this wave and it travels to the right, what we're going to see is that the particles are only moving up and down. They are not traveling along on the track like it were a roller coaster. In fact, they're just moving vertically, perpendicular to the motion because it's a transverse wave. So in this case, if I was going to ask what direction is particle B moving, if this were a roller coaster, it would move down into the valley. But because it's a wave, the wave actually moves underneath it, and B will rise up over the crest coming from behind. So the way we can determine what direction a particle will move as a wave travels beneath it is look behind it. It's a little different to visualize this compared to what we're used to, which is things traveling along a track. A car would travel over hills and move along the hills. In this case, it's as if the car stays stationary and the hills travel beneath it and the car just travels up and down over it. If you envision yourself in a wave pool or in the ocean on a float, you are just going to move up and down as the waves travel beneath you. As a crest comes towards you towards the shore, you are going to move up over the crest and then down into the next trough. So you as a particle bobbing along in the ocean are just going to travel vertically up and down as the wave moves left and right, if you're talking about a transverse wave pattern. Now, that being said, we can use phase to determine the wavelength of a wave. And the definition of wavelength is the distance between two successive points on a wave that are in phase. So it's the next point on a wave that's doing the same thing at the same time. So the wavelength in this example would be noticed by A in this case. It's from crest to crest. If you have a sine graph, it's one complete oscillation up and down of the sine graph. If it's cosine, which is what A would basically represent, it's from crest to crest. Wavelength could also be from trough to trough. Now, if we just go from the midpoint of the crest to the next one on the x-axis, that might be half a wavelength. So wavelength can be measured in whole increments or partial increments. In this case, because we have multiple waveforms, it looks like we have 1, 2, 3, 4 wavelengths represented by the entire wave on the screen. Now, if you were looking at different parts, C would represent half a wavelength, E would represent half a wavelength, and then B and D are there to throw you off. D represents the amplitude of the wave, and then B represents twice the amplitude of the wave. So questions can be worded in different ways, and you could be asked to find different characteristics of the wave based on the information provided. Now, the symbol for wavelength is a Greek letter lambda, and it almost looks like an upside down Y that's tilted a little bit. This value is going to represent a wavelength, which is how far forward a wave goes as the wave makes one complete oscillation, completes one cycle of its vibration. Now, with that being said, we come to our equation of the wave, which is V equals F lambda. Or we can rearrange that as V equals lambda over T if we don't have the frequency and instead we have the time period. Now, if you look at V equals lambda over T, basically that's the same equation as V equals D over T. But since we're talking about waves, we have a special way that we write the distance traveled by a wave, and that's lambda. And we have a different way to write the time it takes for a wave to make one oscillation, and that's time period. But our typical equation is V equals F lambda or V equals lambda over T. The V is the speed of the wave, lambda is the wavelength, F is the frequency, and as long as we measure the wavelength in meters and the frequency in hertz, we'll end up with meters per second. Remember, hertz is 1 over second. If we measure the wavelength in meters and the time period in seconds, and we divide meters per second, we also end up with meters per second. So depending upon the situation we have, we can use V equals F lambda or V equals lambda over T. Now, if you're more comfortable using V equals F lambda, what you can do is, if you have the time period, find the reciprocal of that, and then plug it into the V equals F lambda equation. Most often, I will use V equals F lambda because that's the one I'm the most comfortable with. But you can use either one to solve for the speed of the wave. Or if we know the speed of the wave and the wavelength, we can find the frequency. So depending upon the situation, we can solve for the variable that we're looking for. Now, at this point, I think it would be important to do a couple of sample problems dealing with this equation and solve for different variables within a word problem. So let's look at that now. Thank you. All right, we have different wave characteristics that are going to be important. and we're going to discuss them individually. First, we'll talk about frequency. Now, the two waves that we typically talk about in this course are going to be sound versus light. If we're talking about sound, that's going to be the note or the pitch. If it's light, it's the color. If we're talking about forms of light that are outside the visible spectrum, it could be the type of light that we're dealing with. It could be an X-ray, could be a gamma ray, could be infrared, ultraviolet, etc. But those are all frequencies, and they're measured in hertz, which is equivalent to 1/seconds. Now, it basically represents how often the particles vibrate. So if we had a graph that looked like this, we may have a couple of waves in a pattern, maybe something like that, and this is 2 seconds, let's say. Well, maybe we'll have the same situation, and it does that in 2 seconds. Well, obviously, if we're dealing with wave A and B, wave B is vibrating more often than wave A. But here's how you would find the frequency. The frequency is cycles over second. This particle completes 1, 2. There are 2 full waves, 2 cycles in 2 seconds. So the frequency would be 1 hertz. On the other hand, and this is not the best drawing in the world, but we have 1, 2, 3, 4 cycles in 2 seconds. And this would represent 2 hertz. So if you're given a time scale on the x-axis, you can easily count the number of full cycles you see. It could be half cycles. This, if I stopped it here, this would represent 1.5 cycles. And we think of sine graphs in math class if they start at 0. Each one of these represents a complete sine graph. So this would be the difference between 1 and 2 hertz. That's the frequency. Our next characteristic is phase. And this is not solid, liquid, or gas. It is dealing with the particle movement with respect to other particles on the wave. So, this one is a little easier just to discuss in terms of an example. What I'm going to do is I'm going to letter each section of this A, B, C, E, F. Let's, well, we'll leave the E, and we'll put a D right here. That's what I meant to do anyway. So, according to this diagram, if you're in phase, you're doing the same thing at the same time. Thinking of 2 swings going back and forth together. 2 swings. My hands at this juncture are in phase. If we're doing the opposite, my hands are out of phase. Oh, I wish I were on the swings right now. Out of phase. You could have partial in and out of phase, but eventually you go in or out of phase. Now, in phase, doing the same thing at the same time. A is going to be moving downward if this wave is traveling to the right because you look behind it. B is moving down. C is moving up. D is moving up. E is moving up. F is moving down. So, if we think about this, they have to be doing the same thing and be at the same distance from the origin. So in this case, in phase, are going to be A and F. They're the only 2 that have the same direction and they're the same distance from the origin. In this case, they're on the origin. On the other hand, there's a lot more that are out of phase. Out of phase is they're the same distance from the origin, and they're doing the opposite direction. So, A and C, out of phase. B and E, out of phase. C and F, out of phase. Now you may be asking, why are B and E out of phase? Well, they're max, and they're both doing the opposite thing. D is not in or out of phase specifically with any other particle, but we could have partial in or out of phase. what we could have, did I skip one? No, we're good. We could have C and E. They would be partially in phase, and we would say 90 degrees. D and E, we'd say 45. D and C, 45 degrees. So they're almost doing the same thing, they're just slightly apart. If you remember from math class, you're basically dealing with the 2 pi radians of the sine graph, but just converting it to degrees. In phase is 0 degrees, and out of phase is 180 degrees. So either they're with each other or against. If you remember, 360 degrees completes the full graph, then 180 is the opposite. This will lead into a wavelength, which we'll talk about next. The next characteristic that I'd like to discuss is the wavelength. And that's how far forward a wave goes as a particle vibrates in one complete oscillation. Also, you can say it's the distance horizontally between 2 successive points on a wave that are in phase. Before we talked about 2 points here and here that were in phase, they happen to be 1 wavelength apart. A single crest is half a wavelength. A single trough, also half a wavelength. The entire distance is a wavelength, and the symbol is the lambda, which kind of looks like an upside down Y. All right, if we remember, our equation is V equals F lambda, or V equals lambda over T, we'll realize that this is basically V equals D over T using the wave characteristics. Now, our problem deals with water waves in a lake, and they travel a distance of 4.4 meters in 1.8 seconds. Period of oscillation is 1.2 seconds. So if I were going to be given a givens list, it looks like I just have D, 1.8 seconds. D, 4.4 meters. And T is 1.8 seconds. But then I have another time, and it's the period of oscillation. Now, if you remember, period is denoted with the capital T. So we have a lowercase t for just time, and time period, which is how long it takes one particle to vibrate once, 1.2. Now, although we have these 2 equations, D and T still work. They're not obsolete. So we could just simply use our V equals D over T equation. 4.4 meters over 1.8 seconds, and that will get us the speed of the wave. Taking the calculator, we have 4.4 divided by 1.8, and I'm getting 2.44 meters per second. All right. Now, I have big T and I have V. Well, if I have that, I can find lambda. V equals lambda over T. 2.44 meters per second equals lambda over 1.2 seconds. And I calculate 2.44 times 1.2, and I have my lambda to be 2.93 meters. A little combination of old school equations, V equals D over T, and our new school equation in wave language, V equals lambda over T. It would have to specifically say wavelength to have this D turn into a lambda. So the fact that they just said distance, that's why it's D and not the lambda. So there's a sample problem using our new equation.